Okay, so everybody can hear me. So today we'll be talking about speed scaling. It's an extension of what we've been doing for last 3 lectures. So previously what we did was we looked at the scheduling problem when there were m identical servers with fixed speed, and in particular we took speed to be equal to 1 unit speed, and we showed something. It's kind of negative result that no online algorithm, that any online algorithm has a competitive ratio that scales as log of n by m as well as log of w max over w min. So here we'll allow an extra flexibility. So we still have m servers which are identical, but each server has tunable speed. So each server that you can select its speed. So now if I don't say anything more, you would just like to operate at the maximum speed possible to minimize its flow time. So to attribute an appropriate quantity to capture the speed, what we do is that there is a power function, which is P of S, where if S is the speed of operation. So each server has an associated power function, which is P of S, where P of S is non-decreasing and generally taken to be convex. So non-decreasing, convex. So one simple and popular example is P of S equal to S to the power alpha, where alpha is typically taken to be greater than 2. So now what do we have? So we have on now two sides to the coin. One is the flow time. So to minimize flow time, we should operate the servers as large a speed as possible. And then there is energy, that because of the power function, we are also spending energy to operate at a particular speed s. So energy is nothing but so if s of t is your speed of the server at time t, the integral over the power is essentially the energy. So there is a nice trade-off now, that flow time will reduce if you increase the speed, but energy will increase if you increase the speed. So you can now try to formulate a problem which trades off flow time and energy. So you can either say minimize energy subject to flow time being less than some quantity, let's call it some tau, or you can say minimize flow time subject to energy being less than some kappa. So there are many ways in which you can do it. One simple way, or the more popular way, is to minimize a linear combination or simple combination of energy plus the flow time. So minimize this with respect to s of t. That's the only variable we got. Now there are connections to these problems to this as well. And if you know Lagrangian theory, you can see where these are connected. If you were to plant a lambda here, you would be able to connect the two problems above here with respect to this. So you can do this easily, but for the time being, we're going to reduce lambda equal to 1. That you can do easily. So the problem of interest for us is going to be energy or flow time plus energy problem. That's what we call it. So flow time plus energy. Is the problem clear to everybody?
Yes.
Any questions?
So last in last class we saw that if we increase speed by 2 minus 1 by m,
Right.
then we have optimal flow time.
So that was not increasing speed. That was just changing the speed of the server to be a fixed speed, 2 minus 1 by m. So throughout the time, the speed will be chosen to be 2 minus 1 by m for the SRPT. Then the flow time will be identical to the OPT's flow time with unit speed m servers. So there is no tunability there. We are just increasing the speed of the server while keeping it fixed. Here, at each time t, you are allowed to choose whatever speed you want, and you pay an appropriate cost of p of s of t. So here, this is a over time a decision. So that's why I've written the decision variable to be s of t, not s. So there is a big distinction between what we did last time to this problem. So there is this now a time dependent variable s of t which controls the flow time and the energy, and you would like to minimize the sum of the two. Is the distinction clear?
Yes.
Pranshu, Praveen, the problem is clear?
I have a question. How do you add energy and flow time? Like,
Right. So that's why this lambda will play the exact role of scaling it up. So you have two different distinct quantities. Now the lambda will make sure that you can value them differently. So if you value energy a lot more than flow time, then lambda will be small. And if you value flow time more than energy, then lambda will be large. So as I said, these two problems are related to each other. That if you want to minimize flow time subject to energy constraint, essentially what I'm doing is I'm just moving the constraint to the objective function with an appropriate Lagrangian variable. So they're not very different. They might look very different. Does that answer your question?
yes.
Ravi, problem clear? What we need to do?
Yes, sir.
So now, once again, we'll first look at a single server problem. This itself is non-trivial. Unlike the previous case with, so we'll just remark with fixed speed servers, we know that SRPT is optimal. There's nothing more to be done. Now with variable speed server, SRPT is still optimal. So that you can argue very easily that the scheduling algorithm is still SRPT. What speed to choose at each time t? So what speed to choose at each time t given the state of the system, given the number of outstanding jobs and their remaining sizes. Is not obvious. So essentially what we are going to do is we will consider SRPT as the scheduling algorithm and now try to propose a particular speed and show that with that speed we can get some competitive ratio. All right. So before that, some formulation or like what we are trying to do, formulation issues. So cost as before, so cost of an online algorithm A is going to be flow time plus energy. Now, in terms of our variables, this is going to be, we have done this before, n of t, where n of t is the number of outstanding jobs at time t, plus integral of p of s of t dt. So this is the cost of an algorithm. Similarly, this is the cost of an OPT. And mu a is going to be max over sigma, the input, CA. So let's call it sigma. Sigma over COPT of C. Okay. So here is the recipe of how we are going to bound the competitive ratios. So this is particular to when the objective functions are in integral form, the following recipe is very useful. Okay. So let n of t be the number of outstanding jobs with the algorithm A, and n0t is similar quantity for OPT, and sk of t. So for the moment we have a single server, so that doesn't matter. So s of t, speed of a at time t, and s0 of t. Okay, so now what are we going to do is magically do something like this. So let phi of t be a potential function, some function essentially which you are going to call, it's a name, it's not, we have seen lots of potential functions before. Some function phi such that it satisfies two properties. One, before any job arrives, so it will be a function of the jobs. Okay, so that's why the following two properties are important. So before any job arrives and after all jobs are finished, phi of t 0, or you can equivalently say phi of minus infinity 0 and phi of plus infinity is 0. Two, this is more important, phi of t may have discontinuities but does not increase on any discontinuity. So it's not allowed to jump up. It's allowed to go jump down if it wants on any discontinuity. So this is the requirement for such a function. We have no idea what this function looks like for the moment. So let phi of t with such function with following two properties and the following relation be true. So what is that? That instantaneous at time t, n of t plus p of s of t. So this is the instantaneous cost of a plus the derivative of, so these are for all times where derivative exists, it is less than equal to c times a similar quantity for the OPT, instantaneous cost of. Okay, so let this be true. What does it tell us? That given,
so this relation has to be true only when this derivative exists.
yes. So essentially we are claiming that the derivative exists almost everywhere except at some zero mass discontinuous points. All right, so these conditions are clear now, that phi of t before all jobs arrive and after all jobs depart should be 0, and phi of t should not increase on any discontinuity. So then if you integrate this equation,
So why such a function should exist?
no idea. If it does, then it's useful. Does it do it? We have no clue.
Okay.
For the moment, it's just a recipe. It doesn't tell you how to construct, does it exist, nothing. All it says is suppose such a function exists with these three properties, 1, 2, and 3. Okay, it says nothing about its existence or how to construct it. So now you're going to integrate this equation 1. What does it tell us? Integration this plus p of s of t dt plus d phi of dt dt less than equal to c times integral n0 of t plus p of s0 t. So what can you say about this quantity under these two conditions? See, the two conditions are phi of plus infinity is 0 and phi of minus infinity is 0, or before any job arrives and after all jobs depart.
This is 0.
Right, and there is no jump up. It could jump down. So it never increases up. So using your high school calculus, what you can say is, so now with the integral, this is nothing but the cost of A. With the integral, this is cost of the OPT. And this implies that CA equals to C times COP. Therefore, the competitive ratio A is at most C. So this is the recipe. Any comments on the recipe? Kumar, Pranshu, any comments?
It's fine.
It's fine.
Have you seen this before ever? Most likely no. So this is useful only when the objective functions are in an integral form. Otherwise, it's not very useful, this particular strategy. But when it is, it's very powerful, as we will see. Okay, so now the question remains, does such a phi even exist? See, also phi comes with a, let's call this little c, a little c pair. That c could be arbitrarily large. We don't want that to happen. We want c to be small with small c. And two, how to construct. So this is the broad strategy we are going to follow. We'll look at the single server case and then try to construct a phi such that all these properties are true, and then say something interesting. Okay, so single server case. So again, this is an important point that we are allowing preemption. So preemption is allowed, that you can suspend the job and restart it later. It's allowed. And that implies that you can, SRPT is feasible and therefore optimal for scheduling. We still don't know at what speed to run. So now what do we know? At any time t, process the job with the smallest or the shortest remaining time or remaining work. So that we know. What we know at what speed. Okay, so suppose let's do a simple exercise. So suppose all jobs are available at time 0. Okay, so let's say you have job 1 with size W1, job 2 with size W2. They're also W10. So let's say there are 10 jobs and size W1 through W10. So we know that W1 will be processed first. So now if you would like to write the flow time, so flow time plus the energy. This is nothing but integral of n of t plus integral of p of s of t dt. Can anybody guess the speed to operate? So suppose p of s is s to this power 2. It's not difficult to guess. That's why I'm asking you to think about it. So something remarkable is going to happen. Will it matter that what these values of W1 through W10 are?
No, shouldn't matter.
All right. So do you have a good justification for that? That tells you a lot. That is in fact correct. But that's not obvious, right?
There's only one server,
Yes.
so it doesn't matter what the sizes are. It needs to keep working at an optimal speed.
Point you are integrating over the time period, right? The time period during which your process is going to stay less if you are having high speed. However, when you integrate it, the value is going to be.
Those are not the correct reasons. Your answer may be right, but the reasons are not. So what should your speed at time t depend on? So what should S of t in the optimal solution depend on? See, this is a setting where all jobs are available at time 0. So that is why I can do things of this kind. Otherwise, I don't know what the optimal answer is. Only in this setting, I actually can find an optimal answer. So I'm just asking you to think about what would that optimal S star of t, let's call it S star of t, at each time t depend on? Job sizes or number of jobs? These are the only two quantities which you know.
Number of outstanding jobs.
Okay, and why?
Because that affects the flow time. If there are more jobs outstanding, then they'll all contribute to the flow time. We should.
Why? I'm not yet convinced that that is the right. Again, as I said, answer is correct. Why should it not depend on the size? It's correct that it should depend on the number of outstanding jobs, but why should it not be a function of the size of those jobs also? Anyone? Give me a convincing answer that it should not depend on, it should not matter what those sizes of those jobs are. So let's say the following. So given that, so first property is easy to see. Property 1, that any job is processed at the same speed throughout. So any by any job I mean any one job. Any one job is processed at a fixed speed. So we know it's like S1 star T, S2 star T, and so on till S10 star T. Is this property clear to everybody? That why should this be true? That speed should not change during the execution of a particular job. It could change from job to job. And this critically depends on the function P of S is equal to S square. It's a convex function. So if you were changing the speed of a job during its execution, so at certain point you had less speed, at certain point you had more speed, taking the average would not change the flow time, but reduce the energy. So that one can prove directly. Is that okay? Praveen?
Not very clear, sir.
Okay, so let's say this is my job size 1. For certain time, I ran at speed S1. In certain time, I ran at speed S2, where S2 was larger than S1. Okay, so now I can take a linear S1 plus S2 by 2. Okay, so let's say also this is half and half. So now the flow time does not change. But this is W. So okay, I'm avoiding overload of notation. So this is now T1 times P of S1 plus T2 time P of S2, and compare this to T1 plus T2 P of S1 plus S2 by 2. Now, given that P of S is S square, this quantity is lower than this quantity. So without changing the flow time, I could reduce your energy if you were to choose two different speeds. And the same argument can be continued for more than two speeds. So that argument is easy to make, that any job is going to be run at a fixed speed. So this is going to be S1 star T, S2 star T, S10 star T. Now question is, what should S1 star T depend on? So let's look at the effect of job 1 on flow time plus energy. So W1 by S1 star, let's just call it S1 star. What is this quantity?
Flow time of job 1.
This is the flow time of the first job. But because of this, how many other jobs are getting stopped? 9 of them.
And
So 10 times this is actually the flow time contribution because of this job. Correct? Plus, how much is the energy cost?
S square into W1 by S2.
So this is the energy cost for the job 1. Similarly, you will get S2 star plus W2 by S2 star, P of S2 star, and so on. So each of these jobs are going to get, so you'll essentially get W1 out, and you'll get 10 by S1 star plus PS1 star over S1 star. And similarly, you will get, so W1 will not matter in finding the choice of S1 star. And if you have noticed from here, minimizing, in particular 10 is N of T by Si star plus P of Si star over Si star. The optimal Si star is going to be P inverse of N of T. So in the setting when all jobs are available at time 0, it's not very difficult to find the optimal speed. Are people with me here?
Yes.
Yes.
Okay. So now what our algorithm is going to do is going to assume that at each point T, so now we are in the online setting. Look at a time T. You have current set of jobs which are N of T. Assume no further jobs arrive. So assuming no further jobs arrive, the optimal speed is going to be P inverse of N of T. Okay. So the choice the algorithm is going to make, so choice of speed of the algorithm is going to be P inverse of N of T plus 1. So that plus 1 is just for analysis purpose. There is no good reason for that plus 1. In general, we have been able to avoid this plus 1 also. But for the moment, we are going to choose the speed to be P inverse of NT plus 1 in the online setting. I've given you good motivation that why P inverse of N of T makes sense. That plus 1 is only for analysis. There is another way of interpreting this choice of P inverse of N of T. So suppose S of T is P inverse of N of T. Then what is P of S of T? So P of S of T is simply N of T. So the instantaneous cost is nothing but N of T plus P of S of T, right? Which is equal to N of T plus N of T. So this choice also balances the two costs which contribute to the overall cost of an algorithm. So at any point of time, the instantaneous cost is nothing but 2 times N of T for the algorithm. So that's another way of looking at the speed choice. All right. Any questions at this point? So now we know the algorithm we are going to analyze is SRPT for scheduling and S of T to be P inverse of N of T plus. That's it. This completely defines my algorithm. No questions? So all I remain to, I want to now construct, following my recipe, construct the potential function phi. and an appropriate constant C for which phi and C pair satisfy all the properties that I want. So theorem. The proposed algorithm is 3 competitive and surprisingly independent of the power function P of S. So importantly, independent of power function. This will not hold true when we go to multiple servers. It's only for a single server we'll be able to show that the competitive ratio is independent of the power function. So assumptions to prove this will be on the power function essentially. So let P be a function from R plus to R plus, be differentiable, strictly increasing, and strictly convex. Moreover, P of 0 is 0 and limit strictly increasing will automatically mean this. All right. And remark is all these assumptions can be relaxed. So for the moment, we're going to prove it under these assumptions, but you can actually relax. And the most important one is that even if there is an upper bound on the speed, this is the most important one. See, the algorithm we have chosen for ourselves right now is P inverse of NT plus 1. So if NT grows, the speed also grows. But suppose there is an artificial constraint that a processor cannot work at a speed larger than some upper bound. In that case, also an appropriate change to this algorithm, where essentially you will just do P inverse of NT plus 1, comma, the maximum, let's say S max, bin of the two. This will essentially give you the same result. So this you will prove in homework. It's an interesting observation. Okay, so now the proof. And the most important part of the proof is to construct phi of t. So before that, let's just try to define certain quantities. So stay with me. These are quantities slightly difficult to parse. So as before, n of t will be the number of outstanding jobs with A, and n0t its counterpart of OPT. Now we are going to define a new quantity which is n of t comma q. So this is the number of jobs with A at time t with remaining size at least q. And similarly, we'll define n0tq for the OPT. Is n of tq clear? So n of t is just the number of outstanding jobs with the algorithm. N of t comma q is the number of outstanding jobs with the algorithm at time t with size at least, or the remaining size at least q. So let's look at a picture. So suppose n of t is 4. Okay. And the y-axis here depicts the remaining size of these 4 jobs. So this is the remaining size. So what does essentially this q is doing is, so this is, let's say, q0. q1. So each value of q, we are defining this. I'm just drawing it for certain values, q3. So how much is n of t comma q0? Is all of them, right? The remaining size for all the jobs is at least q0. So n of t comma q0 is 4. How much is n of t comma q1? This job, this particular job here, has remaining size less than q1. Rest of them have size at least q1. So this is 3. And similarly, n of t comma q2 is 2. And n of t comma q3 is 1. Is everybody okay with the definition of n of t comma q?
Yes.
It's just the you can it's not histogram, it is the frequency of how many. It's like CDF or inverse CDF, if you know what I'm talking about. So that's what this is. Now using this quantity, we're going to define a function d of t comma q, which is going to be the difference of, for each, again this is for each q, max of n of t comma q minus n0 of t comma q. So this is the difference between the algorithm and the OPT max, just to make sure that it never goes negative. All right. So this for the algorithm and this is for the OPT. So you can think of amount of work left with the algorithm and amount of work left with the OPT for each q. And here is my definition of phi. So phi of t is going to be some constant c, which will essentially reflect our competitive ratio bound, integral with respect to q, f of dtq. This is my potential function phi, where I am yet to define what is my f. So f is a function which is f0 is 0, and for I greater than 1, delta I is f of I minus 1, and delta I is nothing but p prime of p inverse of I. So it's slightly convoluted defined, but if you see it carefully, so what does this quantity mean? That p prime is the first derivative. So p prime of x is nothing but, so you, is this quantity clear? P prime of p inverse of I. You just plant, so you think of p prime of x where x is equal to p inverse of I. That's what this means. Is this function clear? F and then phi of t.
Yes.
Praveen, is this clear? Kumar,
Yes, sir.
is the definition clear?
I'm still looking at f. So how to get f from this?
Right. So think of delta I. So f of 0 is 0, right? So starting point is clear. So you know what is delta of 1, which is f1 minus f0. So f1 is nothing but delta 1. So f0 is 0, f1 is delta 1, f2 is delta 1 plus f of 1, and so on. Everything well defined?
Yes.
Okay. And all these are integers. So d of tq is either 0 or an integer. So this is my potential function. Any comments on it? Like, what do you think is going on here? See, remember, what are we interested in? We're interested in the derivative of this function. So what will be the derivative of this function is what is our real interest. So any guesses to what the derivative of phi of t will look like? It's not a difficult quantity to see. So just look at time t and time t plus dt. What changes among all these things? F is a function, so that doesn't change. Which quantities change between time t and t plus dt?
D of t comma q can change.
Right, and how does that actually change? One because of the algorithm and one because of the OPT. So what does algorithm do to DTQ?
Minimizes.
No, there's no minimization. What is DTQ? DTQ is nothing but, forget the max, it's just the difference between NTQ and N0TQ. So among NTQ and N0TQ, which quantity is affected by the algorithm?
NTQ.
NT.
Right, and what is happening to NTQ at between time t and time t plus dt?
Either it remains same or decreases.
Why should it ever remain same?
So if the job does not get complete,
No, think about it. That's why that quantity has been defined very carefully. What is n of t comma q?
it will depend on Q.
No, so your earlier observation that if the job completes is when I don't have to contribute, that's not correct. So which job is being processed by the algorithm?
Which the smallest job.
Smallest job. So let's say the smallest job size is QS. So no matter it's completing or not, the algorithm is always processing the job with a particular speed. So between time t and time t plus dt, how much amount of work is done on the job? S times dt. So QS goes from QS to how much? So for the algorithm, so it's an aside. Let's consider algorithm A, which working with speed S of t, and QS be the job, be the size of the smallest job. So QS of t be the size of the smallest job. Right? So then between time t and t plus dt, what happens to n of t comma q? See, this is a function defined for all q. Just tell me for which q it gets affected and by how much. Just to remind you, n of tq is the number of jobs with size at least q. So which job is getting processed by the algorithm? The smallest job. And the size of the smallest job is QS of t. So every other job has a size which is larger than QS of t. Agreed?
Yeah.
So for which values of q does NTQ change in interval t to t plus dt?
Q is less greater than QST minus S times dt.
Sorry.
If Q is greater than QST minus S times dt.
Okay, I have written half the answer for you. So just tell me for what interval of q does NTQ become NTQ minus 1? See what is happening, that I have a certain level of a job which is at present QS of t. In time dt is going to go down by QS of t minus S of t dt. So one job is going to move below the level I am counting for. So which levels I am counting for is being captured here. For all other queues, NTQ will remain the same.
Yes, so Q should belong to QS minus ST dt to QST.
QS T minus
STDT.
Does everybody agree with this? And NTQ is equal to NTQ for all other. See, this is the important property of the algorithm, that I am working on the shortest job. So only for certain values of Q, which are the smallest at the level, n of TQ is going to go down to n of TQ minus 1, while for all others, n of T comma Q will remain as it is. Is this clear to everybody? Now using this, can you tell me what will be the derivative of this function phi of t? Now it's not very difficult to say. In terms of delta, if you want. So in small time t and t plus delta t, how does the difference of phi t and phi of t plus phi of t and phi of t plus dt look like?
So f is increasing function. So
No,
if
f of I minus f of I minus 1 is defined to be delta of I. So you can use that. So in terms of delta I, can you write the difference in phi between time t and time t plus dt? We have exactly written down that for certain values of q, n of tq goes down exactly by 1. And the same thing happens for OPT, because we know that SRPT is an optimal algorithm. SRPT is just using a different speed possibly, knowing what jobs are coming in future. So the same thing is true for OPT also, where it might be working on Q0 of t. So Q0 of t might be the job with the smallest size with the OPT. So what is d of tq and d of t plus dt comma q? The only change is for the algorithm for these values of q, and similarly for the OPT for q0t minus s0t dt and q0t. There is no other change. So you will get one term for the algorithm and one term for the OPT, but both will be in terms of delta of something. Is at least that much clear? We'll do this formally. Pranshu, is this clear that one can write the difference in terms of deltas?
Sir, could you repeat it? My internet froze for a second.
So should I go back to this computation or just ask the question?
Just the question.
So question is, can I write the difference of phi of t and phi of t plus dt as a function of delta of something?
Yes.
See, now given that I have written this and this, similar thing holds for d of t comma q, that this goes to either plus 1 or minus 1, depending on I'm looking at OPT's contribution or algorithm's contribution. If I'm looking at algorithm's contribution, dtq goes to dtq minus 1 for a certain value of q. Otherwise, dtq goes to d of tq plus 1 for the OPT, because this is in the negative here. So n0 tq is going to go down. So d of tq is going to go up. So in both cases, I should be able to write down the difference of phi of t and phi of t plus dt as some function of delta of I or minus delta of some I. That is what I want to. So this is the intuition I want. We'll do this formally, everything. That why we have constructed this function is what I'm trying to get at. That why is this mysterious form? It's actually not a very mysterious form. This f of I minus f of I minus 1 is essentially capturing the rate of change because of the algorithm and the OPT, because in any small interval, d of tq either goes up by 1 or goes down by 1. And that is why it has been defined as a difference of 1, f of I minus f of I minus 1. And the exact value of delta I is chosen here for some lemma to be applied. So that is another reason why this is the particular choice. But at least this choice should be clear that why are we doing this? Was it helpful or not really?
D of tq could remain constant also if both change the same. If ntq and n0tq change by the same amount.
Right. So suppose n0, see, they only can go down. So
Yes.
difference can either be how much? So both go down for the same value of q, but that's very unlikely. We'll take care of that also.
Okay.
Right. So this is an integral outside for q here. So we are going to look at what is the operating point for the algorithm, by which I mean what is the smallest remaining job size of the job being processed by the algorithm, and similarly for the OPT. If they're identical, then we'll worry about them separately.
Okay.
Okay, so now given that we have a long discussion on the intuition, let's check the first technical condition. So boundary condition. So what is the first boundary condition we need to check? That before any job arrives and after all jobs depart, phi of t should be 0. So does that satisfy?
Yes. N of tq is equal to n0tq at the beginning.
So yeah, so before any job arrives, d of tq is 0, and after all jobs depart, again d of dtq is 0 for all q, and f of 0 is 0. So the whole integral is 0. Now the second technical, so first is easy. 2, that phi of t does not sorry. So what are the points of discontinuities for phi? There are only 2 types. Just look at it carefully. Phi of t is nothing but a function of n of tq minus n0 of tq. Now, when do n of tq and n0 tq change discontinuously?
Discontinuity with respect to time. Right?
Yeah. See, f is a function, so that is not a problem. F is a continuous form. Only discontinuity will come if n of tq or n0 of tq change discontinuously. And when do they do that?
When exactly one of the NTQ or N not TQ decreases.
That's not true, right? When a job is getting processed at a fixed rate. So that's not a discontinuity. What about a job arrival? What happens when a job arrives?
So both increase by
No. Is that the point of discontinuity is the question. So we're just trying to identify what are the points at which there can be a discontinuity.
So at job arrival, there is no discontinuity because both number of so NTQ and N not TQ will be same for.
No, that's you're jumping one step ahead, but that's what I term as a discontinuous event possibility, that an arrival of a new job or a departure of a job with either the OPT or the algorithm. These are the only possibilities where discontinuity can arise. Everywhere else, the algorithm as well as the OPT are just processing jobs, right? And that is not discontinuous. So the only discontinuous events are the points of discontinuity, arrival of a job or departure, which can happen differently for algorithm and OPT, departure with algorithm or OPT. So now I think Kumar.
Here departure means that size decrease is smaller than Q.
No, departure means the job is complete and it departs the system.
No, but we are only looking at jobs with size at least Q. So
Yeah.
departure should mean here that now job size decreases below Q.
0 or becomes equal to 0. So just before 0, there is a small change, right? Whenever a departure happens, at time t, the job had a non-zero size. At time t plus dt, it became 0 and it just departed. Correct?
But if the job size is smaller than Q, then we are already not counting it.
What does it mean by smaller than Q? Q is for
So-
all Q. So this is defined for all Q.
Okay. No,
Q
so
is,
but
there
we
is,
are only looking at time T.
what
I
are we
mean,
looking at?
we are only looking along time axis
No, for
for
each,
discontinuity.
yeah, for any one particular time t, I'm looking for discontinuity. Is there a discontinuity or not? Now, what could give rise to discontinuity? Either an arrival of a new job or departure of a job with the algorithm or the OPT. So I don't think you have understood what this function dq looks like. So this is for a fixed, so this is time axis. At each time t, I'm taking the integral with respect to all q. Different jobs have different sizes. So this function gets evaluated as an integral with respect to q. So
Okay.
for all q, d of tq is well defined. Maximum value is n of t, minimum value is 0.
Yes.
Right? So this integral is a well-defined quantity for each time t. Now, question we are trying to ask is there a discontinuous event, discontinuous time at which phi of t jumps? If it decreases, I don't mind. So now tell me, when a new job arrives, as you already said, both this quantity and this quantity increases by the same amount. So d of tq doesn't change. So there is no jump. But now look at the departure times. They happen separately for different jobs. They don't happen simultaneously for both the algorithm and the OPT. So now can you convince me that phi of t does not increase on a departure time, either with the algorithm or with the OPT? Is the question clear to everybody? Is the question clear?
Yes.
Oh. Does the question make sense?
I mean, yes, we need this because I mean this is required for the recipe.
Right. So now think about when a job is departing the system, what is happening to it? It's very near to 0, right?
Yes.
So now just make a simple argument about phi of t. And that is why it's an integral, not a summation.
Okay.
Does that hint tell you something? It's an integral with respect to d of q. So a job which departs changes any, if at all, essentially at q equal to 0. But that does not change anything with the integral.
Yes.
Yeah.
So departure of algorithm, departure of anything only change in d of tq happens at q equal to 0. But because of the integral outside, phi of t remains unchanged. So each of these things have been carefully kept in mind while designing this particular function. You could have said, I will say that this function is nothing but a summation for q greater than some intervals possibly. Then this function will not have this property. So you can define this over intervals of q's rather than an integral. There you will actually have a problem. Okay. So both the first and the second condition are actually true. Now what do we need? So finally the drift condition. That n of t plus p of s of t plus d phi of dt by t should be less than c times n0 of t plus p of s0 of t for all t. This is what we need to show. So essentially we need to control how small this quantity is. So what is d phi of dt? Is negative because of algorithms processing, and positive because of OPT's processing. If you see, phi of t comes down, is going down as algorithm is processing jobs by bringing down n of t, and it goes up because of the negative sign when n0 of t decreases, which is the processing of the OPT. All right. So now we are going to look at both these conditions, that how much is the negative drift, how much is the positive drift, and try to account for both of them. So case 1, where n0 of t is greater than n of t. That is number of jobs or number of remaining job. OPT is strictly larger than number of remaining jobs. Okay. I claim that in this case, d phi of dt is less than equal to 0. So for the moment, assume that this is true. Then we show that our drift condition is true. So what is our P of S of t? By our choice of S of t is equal to P inverse of nt plus 1. This is at most nt plus 1. And d phi of dt is less than 0. So this quantity is at most this quantity. And given that n0 of t is greater than n of t, we get that this is at most 3 of n0 of t. So drift condition is true for c equal to 3. Is everybody with me? I'm yet to prove that this is true. So if the derivative of phi of t is less than 0, then I have that the drift condition is true for c equal to 3. Everybody fine?
Yes.
Okay, so now tell me why it should be that in this particular case, when the number of jobs with the OBT is larger than the number of jobs with the algorithm, the d phi t of dt should be less than equal to 0. Just go to the definition of the algorithm. Sorry,
d
Pranchu.
of, d of tq is 0 in this case because we are taking max.
D of tq, remember, is max of 0 comma n0 of tq minus n of tq minus n0 of tq. Okay, what were you trying to say?
So
All I know is that n0 of t is greater than n of t. This is all I know.
d of tq could be 0 for,
Why?
so we don't know if n0 of tq is greater than n of tq. For,
Yeah, so, but think about it. You're on the right track. So let's say Q0 is the smallest size of job. And QA be the smallest size job. with A. So by definition, what is N0 T equal to? N0 of T comma Q0, and by definition N of T is N of T comma QA. This is just by definition, right?
Yes.
Everybody remembers the definition of NT comma Q, right? If you look at the smallest job, N0T is nothing but the number of jobs greater than or equal to the smallest job. So N0 of T comma Q0 is equal to N0 of T, and N of T is equal to N of T comma QA. Now you can say whatever you want to say. So all I'm given is this condition is true. So that means N0 of T comma Q0 is greater than N of T comma QA. This is known. So now you can take the condition Q0 being greater than QA or Q0 being less than equal to QA. Now what happens? So in one case it's easy, other case also it's easy.
Because SRPT processes the smallest job and it has fewer number of jobs than OPT.
Yeah.
Uh, so and so for any Q, this NT and not TQ should be greater than NTQ.
That's not true, right? Just think about like OPT has 10 jobs. Algorithm has 9 jobs. Okay. Now let's suppose the first 9 jobs are of size 1 and the last job is of size 0.5. Here it could be anything. I don't know what it is. So let's suppose the first 8 are of 1 and the last one is 0.4. This is possible. Even though N0 of T is greater than N of T. Sorry?
Our algorithm can't be better than the OPT, right?
No, at a certain point, OPT is doing something crazy. Who knows? We're not making any assumptions on what OPT is doing. We're not making comparison between the set of jobs OPT keeps or set of jobs algorithm keeps. This is quite possible.
Okay.
No, so here algorithm has 9 jobs as you gave example, but for any Q, this NTQ is less than N not TQ. I mean, we can see from this example also.
But that's not true. I can give you an example where that is not true. There are certain values of Q for which that is not true. I can just increase the size of some, make it 2 and 2 here.
So for so this 2 and 2 will be there in OPT as well.
No, who says? All we are comparing is numbers. We are not comparing set of jobs.
Okay.
All we are saying is that the number of jobs with the OPT is larger than number of jobs with the algorithm. That is all I know. I don't know their sizes. But still, you should be able to say that d phi of dt is actually less than equal to 0. So why don't you think about this one case and this one case? So when Q0 is greater than QA, what happens? I know already this is true.
Then for all,
Don't say for all Q.
no, for all Q greater than Q naught, N0 of T is greater than N of T.
Okay, so think about, is this statement correct following the above? That N0 of PQ is greater than N of TQ for Q belongs to Q0 minus S0 of t dt, comma Q0. Irrespective of, let's call it 2 and let's call this 1. Is this statement true? Given that,
Yes. Yes, I mean this should be true for Q belonging to QA to Q not.
why are we bothered about that?
No, I mean yeah.
Is this statement true or not?
Yes.
And why?
Because still n naught jobs, so n naught TQ is still equals to n naught n naught T, and NTQ is less than NT.
So in one case it is obvious, other case you have to work a slide. Okay. So let me stop at that. So suppose you're given this. Why does it imply that d phi of, so we still have to say that d phi t by is less than equal to 0. So suppose you're given this. Now what can you say? So what, so at time t, we know this is true. So what will be true for time t plus dt? So remember, this is strict inequality, and n and n zeros are integers. So we know that n0 of t plus dtq is greater than equal to n of t plus dtq. Why is this? Anybody? So given that this is strict inequality and n0 and n such integers, what we know is that n0 of t comma q is at least n of t comma q plus 1. And in small interval t plus interval dt, n0 of tq could come down by 1 at most. So that is why this becomes an inequality now. So at time t we have this, at time t plus dt we have this. So the OPT's contribution to d phi t by dt is less than 0, and algorithm's contribution we don't even count since it is always less than 0. Therefore, d phi t by dt is less than 0 if n0t is greater than n of t. Is everybody happy?
Yes.
So from here to here, I've just used the integrality of n and n zeros. That's all I've used. That if at a time t, n0 is strictly greater than n, that means that at time t plus dt, it can at best be equal to n. So just looking at the OPT's contribution, d phi t by dt is less than equal to 0. Algorithm's contribution is always negative. So I'm just going to not even count how much it is, because all I need to show was that it is less than equal to 0. All right. So now we're going to look at the second case, case 2, where n0 of t is strictly less than n of t. The equality is falls in between. So either of the two cases imply. So we don't have to work too hard for that. So here we have to look at case A, B, and C. So case A is QA less than Q0. Remember, for the OPT, smallest job is size is, and algorithm QA is the smallest job size. So when QA is less than equal to Q0, algorithm, this we have done before, changes n of Q or t comma Q to n of t comma Q minus 1 for Q belonging to QA minus SA TDT, comma Q. Right? Everybody is with me on this? That this is what the algorithm is doing. because it's processing the smallest job, which is of size QA at speed SA of t. So the algorithm's contribution is d phi is equal to C times f of NQA. I'm dropping the t here so that I don't have to worry about this. Minus N0 of QA minus f of N of QA minus N0 of QA. Does everybody see why this is correct? Times SAT dt. Kumar, is this okay? What was our phi of t? F of dtq dq, and dtq was max of 0 comma ntq minus n0 tq. So we are first looking at q around this interval, and that is what the difference of the integral give you. So this is because of the contribution by the algorithm. So using the definition of delta, I can write this as C times del minus delta n of QA minus n0 of QA st dt. Now I'm going to write something. So justify this for me. N of t minus n0 of t. Can somebody justify this? Remember, we are in this case. QA is less than Q0. So what is n of QA? It's always n of t, because I am always working on the smallest job. Correct?
Yes.
So n of t comma QA is always n of t. That's not a question. Why is n0 of QA equal to n0 of t? Because QA is less than Q0. So this implies that this is true. All right.
Yes.
So now we're going to count the contribution of OPT. It's very similar to before, except with a positive sign now. So d phi of t will be C times f of n of Q0 minus n0 of Q0 minus 1 and minus f of n of Q0 minus n0 of Q0. Now S0 of t to t. So this is now positive delta C times delta n of Q0 minus n0 of Q0 plus 1. So this is just by the definition of delta, which was fi minus 1. Okay, so we are still in the condition that QA is less than Q0. So how much can you bound this quantity? This quantity is always equal to N0, right? What about this quantity? N of Q0. If this is true, can you relate these two quantities?
N of Q0 should be less than N of
Q0
should be less than N of, yeah.
That's not quite true, right? Can you say more?
I
See, remember, Q0 is the smallest size with the, and QA is the smallest size with the algorithm. Now I'm counting all the jobs which are above this, right? How many jobs are above this? These are exactly N of t. But how many jobs are above this level at most? Is this picture clear? By definition, how many jobs are, or how many jobs have remaining size at least QA? That is n of t itself. So how many jobs have size at least Q0 when Q0 is strictly greater than QA? This is at most n of t minus 1, right? This job, the smallest job here, that is clearly smaller than Q0. So this is a quantity which is at most n of t minus 1. So if you're combining this here, we get that d5. Was this okay?
Yeah. I mean,
You again get back that it's c times delta n of t minus n0 of t s0 of t dt. So combining the contribution from both the algorithm and the OPT, what we get, the d5 by dt, just moving this t here, is at most c times delta nt minus n0 t minus sat plus s0 t. So this is a common term to both of them. And this is the speed of the algorithm, this is the speed of the OPT. So in other cases also, we'll get something very similar. So I'm not going to repeat them. So QA greater than equal to Q0, we'll get something very similar. You can see it in the notes what exactly you will get. So now the question is, how do I bound this quantity? The right hand side, delta of n of t minus n0 of t times this quantity. I would like, see, remember, what do I want to compare? I want to compare n of t plus p of s of t plus d phi dt with respect to c times n0 of t plus p of s0 of t. This is what I want to compare against. So I want this bound somehow in terms of n0s and p of s0s t. So here is a lemma which we'll prove next time. So lemma that delta of some beta, where beta is greater than equal to 0, times minus s plus s tilde, where all these quantities are greater than 0, is less than equal to minus s plus p inverse of beta whole thing times p prime p inverse of beta plus p of s prime minus beta. So this is a technical lemma which will be proved using Young's inequality. But if you noticed, what was the definition of delta of I was exactly this, p prime of p inverse of I. So this is where we're going to get everything what we want. So applying this lemma here, so applying the lemma, what can we say? That d phi by dt is at most. So remember, just look at the terms. So this is my beta is equal to n of t minus n0 of t. This is how I'm applying. And minus s is equal to minus sa of t, and s tilde is equal to s0 of t. So that is what I'm applying this lemma over. What we end up getting is that minus s of t plus p inverse of beta, which is, let's just put the values there, n of t minus n0 of t times delta of nt minus n0 t plus p of s0 t minus nt minus n0 t. Everybody with me? I've just applied that lemma for beta equal to this and s is equal to sa and s tilde is equal to s0 of t. Now can somebody comment? So what is our choice of sa of t? P inverse of nt plus 1. So what is this sum? Can you upper bound this sum by? Minus sat plus p inverse of nt minus n0 t. Guys, this is easy. Sorry?
So this P inverse NT minus N naught T is at most equals to P inverse NT plus 1.
Correct. And minus SA of t is greater than that. So this is at most 0. So I can get rid of the first term and I can simply say that this is P of S0 of t plus N0t minus N of t. Right? That's all I get. Everybody with me? Okay, so now I can go back to my running condition. That's d phi t over dt. And what is this at most equal to? N of t plus N of t plus 1 minus C times. So there's always a C outside here. Okay, so C times N of t plus C times N0t plus P of S0 of t. So when am I in good shape? So choosing C equal to 3, I can get rid of all these three terms here. So this is at most 3 times N0t plus P of S0. So this is a C equal to 3 choice is made in the potential function itself. So this tells us that the competitive ratio okay, and we are done.